we're going to take a look at something called the law of sines in this video series. And so the law of sines is going to help us to be able to solve triangles that aren't necessarily right triangles. So we're going to use the law of sines to solve oblique triangles. And then we're also going to take a look at something called an ambiguous case, okay, to where we might have more than one possible triangle that arises from given conditions. So let's first of all define some things about triangles, okay? So first of all, let's talk about an oblique triangle. Oblique is any triangle that does not contain a right angle, okay? And so there's two different types of oblique triangles that we're going to be looking at. Three acute angles or one obtuse angle and two acute angles, okay? And this is the one that has the obtuse angle, and then this clearly has three angles that are going to be acute, okay? Whenever we label a triangle, okay, so whatever the angle is and the side, they should be opposite of one another, okay? So this is angle A, side A is opposite of that. If this is angle B, side B is opposite of that, and if this is angle C, then side C is going to be opposite of that, okay? Every single time for every triangle, okay? So that's standard when we do these, right? Now, our job is to be able to use some information that's preliminary about either of those triangles and to be able to find the rest of the components of the triangle. And we're going to be able to do that by using something called the law of sines. And the law of sines states that the ratio of the sides and their corresponding angles are the same. Okay, so basically, if I take the sine of an angle and a side that's going to be the corresponding opposite side, that's going to be equal to the sine of another angle and its opposite corresponding side, and the sine of the third angle and the ratio of that and its other corresponding opposite side. Or we could just take the reciprocal of all of those and just have, and this is the version I prefer, sine A over A, sine B over B, sine C over C. Now, let's verify this, okay? The law of sines is actually fairly easy to verify. So notice that we have the same triangle, ABC, okay? So these are both triangle ABC, or capital ABC, excuse me, because the angles are capital. So, but we just go through and we take a look at two different hypotenuse, okay? So we have a hypotenuse here and a hypotenuse here. Just assume that they're going to be the same measure, okay, which they are in this diagram, all right? Let's take a look at the first triangle, okay? And what I want to do is I just want to pick this triangle really quickly, okay? And I want to find the sine of B. So the sine of B is going to be equal to, remember, sine is opposite over hypotenuse, so that's H over C. Or if I multiply both sides by C, C sine of B is equal to H, okay? So now let's do the same thing with C, okay? So let me take a look, and I'm going to use a different color this time, right? And let's take a look at this triangle, okay? And so if I took a look at angle C, the sine of C would be the opposite, which is H, divided by the hypotenuse, which is B, okay? Or we could multiply both sides by B, and we would get that B sine of C is equal to H. And notice that since these are both equal to H, we could set these two expressions equal to one another, okay? And so if we did so, we would get that C sine of B is equal to B sine of C, and I could divide both sides by BC if I elected to, right? Notice that on the left-hand side, the C's would cancel out, so I would have sine of B divided by B. And on the right-hand side, the B's would cancel out. I'd be left with sine of C over C. And notice that's actually one of the components right here, that sine B divided by B is equal to sine C over C. Okay, so we've actually proved that ratio, and we're going to use the second triangle to be able to prove the other ratio. All right, now let's pick one this time, maybe A. Okay, so I'm going to take a look at this triangle, this smaller one. Okay, and if I want the sine of A, that's going to be the opposite, which is H, over the hypotenuse, which is C. Okay, or another way to write that would be C sine of A is equal to H. Let's take a look at the triangle that contains angle C in it. Okay, so something like this. Okay. So if I had the sine of C, that would be equal to the opposite, which is H, divided by the hypotenuse, which in this case is going to be A, or A sine C is equal to H. Now notice again that those are both equal to H, so we can take those two expressions and set them equal to one another, right? And so we would get C sine A is equal to A sine C. I could divide both sides by AC. And so what we would get, C's would cancel out. I'd have sine A divided by A, and then the A's would cancel out, and I would sine C divided by C. All right. Now notice that sine C is also equal to sine B over B. Okay. And so that would be the same thing as sine of B divided by B. Not sure what happened here. Just decided to go away. But there we go. And this is precisely the law of sines if I were to just flip those two around by transitivity that's valid. Okay, so that's how we can prove the law of sines. Okay, it's actually pretty easy for us to prove what the law of sines is. Okay, all right. So now that we know the law of sines, and now that we know the proof for it, in our videos, the remaining videos for this section, what we're going to do is we're just going to use the law of sines. Okay, so we're going to see at the beginning it's fairly easy. There's going to be something called an ambiguous case, which is a little tougher. Um, but overall, this is more of just making sure that we can set up our ratios correctly. And then once we do that, just using the sign of the function to be able to evaluate and approximate angles and sides for this.